San Francisco State University. She did her PhD at UC Santa Cruz. And before that, she did 2 master's theses, as some of you know, at Santa Barbara and undergrad at UC Santa Cruz. So with that, thank you for being here. Take it away.
Okay, so thank you for inviting me. It's been a nice visit so far. I'm sorry I have to dash off right after the talk, but the 3-hour drive back. So I'm going to talk to you today about the early Pliocene and about the patterns that we can see from the early Pliocene, and a little bit about what the lessons are that we can learn about what a warmer climate looks like. So this is a map of sea surface temperature for those of you that are not oceanography types in the room, which is probably most of you. So I'm going to show you this figure over and over and over again, so let's get used to it now. So, I mean, this is a map that if you've ever looked at maps of sea surface temperature is really familiar, right? You just see the warmer tropics, it's colder as you move to higher latitudes, but there's a couple of other features in this other than those really obvious ones, and they are things like the California current coming down here, this current moving up here, so you have slightly cooler waters here. This is both the fact that you have cold water currents moving down, but also that those areas are characterized by coastal upwelling. So winds moving water offshore, and that bringing up cooler water from below. And that characterizes the western continents in both oceans. And then the other characteristic feature of this is that the sea surface temperature in the eastern equatorial Pacific, so here around the Galapagos Islands, is colder than in the western Pacific. So the difference, the temperature difference between here and here is about 5 degrees Celsius. And that's a sort of a characteristic that's usually there unless it's an El Nino year, in which case that disappears. So I'm going to come back to this figure over and over again. So what I'm going to tell you about first I'm going to tell you about why you should care about the Pliocene, and hopefully convince you that climate 4 to 5 million years ago was actually something that was worth your interest. And then I'm going to spend most of the time of the talk talking about, well, what are the patterns of climate during the early Pliocene, look at the subtropical coastal upwelling regions and the tropical Pacific, and then I'll finish up by talking about, well, what are the implications of that, of those patterns, and what does that tell us about this warmer world. So first, to set up the problem, this is a figure of greenhouse gas concentration. So this is CO2, methane, and nitrous oxide for the last 2,000 years. Here we have the Industrial Revolution. This is all the measurements from within the atmosphere, and then this is all the data from ice cores. And that's, this is a figure that probably most of you have seen. This is the big question in climate is what, we know that this is happening, we know that CO2 concentrations are increasing, and the question is how much warmer is it going to get? So we're actually, May 10th of last year was the first time that the Mauna Loa data went to 400 ppm, and that's now happening more and more frequently, so we're sort of, this is going up and up. So the big question, of course, is how much warmer is it actually going to get, right? So we have CO2 emissions, and we want to know how much warmer it's going to get. So in this figure, this is a figure from the IPCC report. It's actually from the older one. I just haven't updated it yet. But everything to the left of the center line is data. So this is all temperature measurements. And then everything to the right of the line from 2000 to 2100, these are all model results. Okay, so each one of these colors represents a different CO2 emission scenario. So this is, if you're going to model how warm climate is going to get, one of the first things you have to do is make some assumptions about how much CO2 is actually going to increase. And it turns out there's a huge amount of uncertainty in that. Population growth, are we actually going to implement any policies to reduce CO2 emissions, things like that. So the scenarios that I want to draw your attention to are the A2 scenario, the red one, which is commonly referred to as the business as usual scenario. And then this other one that's interesting in this figure is this one, which isn't really a scenario. This model is what happens to a climate model when you keep CO2 concentrations in the atmosphere at 365 parts per million. So we've already gone beyond that, but that was the experiment that they ran. And that was to get a sense of what's the warming that we're committed to, because we're not going to go back below that. So this is sort of the commitment scenario. And then for each one of these scenarios, this represents the full spread in the model prediction. So there's a huge range. So there's a number of these complex models, and the spread of them, when you look at all of the models together, there's quite a range in the model spread. And it turns out that range is due to uncertainties in the feedbacks. So we know the physics of how greenhouse gas works, right? We understand how a CO2 molecule works. We understand that it vibrates, that it bends, that makes it absorb infrared radiation. Those are all things that we have a high certainty for. But the things that we don't have high certainty for are all the feedbacks. What's going to happen with clouds? Are they going to be more reflective? Are you going to have more reflective clouds, or are you going to have more clouds that absorb outgoing radiation? What's going to happen with El Niños? You're going to have more El Niños, bigger El Niños, fewer El Niños. Those things all affect the average climate. So the spread in the models is not related to it's not related to the direct forcing. It's related to the feedbacks and the indirect forcings. So the Pliocene turns out to be a really interesting period of time because it's the most recent time in Earth history that climate was warmer. So we know from the data that we have that average global temperatures were 3 or 4 degrees Celsius warmer. And also we know that CO2 was higher. So this is a figure of atmospheric CO2, so 250 to 450, and this is going back in time. So paleoceanographers always do this. We always put today on the left-hand side, and then it goes back in time in this direction. So back to 6 million years. And these are CO2 reconstructions. So the ice core data that you're familiar with seeing really can only go back about 700 to 800,000 years. Okay? So ice cores are direct measurements of ancient atmosphere, where you're literally just looking at a bubble of ancient atmosphere. But those only go back to here. So these are proxy reconstructions. These are based on the carbon isotopes of alkanones. I'm not going to go into the details of the proxy other than to say that it's complicated. But what we do is we reconstruct it at a variety of different sites. So this is a paper that was published in 2010. Each one of these is a different site. There's Pacific sites, there's Atlantic sites, North Pacific, Tropical Pacific. So there's a variety of sites. And what you can see is that all of them show that CO2 was higher. And there's 2 time periods highlighted. One of them is the mid-Pliocene, and I don't know if people are familiar with the PRISM project. This is a USGS project that has selected a time slice. In fact, that's the time slice right there. And they started this back in the mid-90s. They said, okay, let's look at what climate was like before the onset of Northern Hemisphere glaciation. And they picked this one time slice rather than doing a time series, because they said, let's look at what the spatial variability is in climate. So that's what the PRISM time slice is. I'm mostly going to be talking about climate at around 4 million years, because that's actually the peak in the warming. That's actually the warmest time. It turns out that if we had to redo this, if PRISM had to start from scratch, we would probably pick 4 million years and not this time interval, because we now know that a lot of places were already cooling by the time you got to here. But the point here is that the early Pliocene CO2 concentrations, somewhere between 375 and a little above 400. So they're actually really comparable to today. They're really similar to today. So about 100, 125 higher than pre-anthropogenic PCO2. So, let's see. Okay. So the question then is, we know that Pliocene PCO2 was sort of closer to this level, but actually global temperatures were warmer than they are today. So let me tell you a little bit more about what else we know about the Pliocene. So we know that CO2 was higher. This is the benthic oxygen isotope record of the last 5 million years. This is a global record, a global stack record. For those of you that aren't familiar with benthic isotopes, I just put these indicators on the side here. Basically, so again, we're going from 5 million years on the right to the modern today. As this curve moves towards heavier values, so this is isotopically heavier, what you're seeing is a combination of both increased ice volume and colder temperatures. So benthic isotopes record both of those things. So what you're seeing is a climate here that has, see how the variability is smaller? and then as it moves at around 3 million, you have this kind of big change, and this is the onset of northern hemisphere glaciation. So before that time, there was basically very little ice on Greenland and in the northern hemisphere. And then you transition to having more ice sheets. When you have more ice in the northern hemisphere that's more sensitive to orbital forcing, you start to get larger amplitude variability. It's still on a 40,000 year periodicity, and then here you move into the classic Pliocene 100,000 year glacial interglacial cycles. So the Pliocene was 3 to 4 degrees warmer than today, and it is the most recent period of sustained warmth. I mean, you could argue a little bit that some of these interglacials might have been a tiny bit warmer than today, but it is the interglacials, other than the Holocene, were actually pretty short-lived. And so the Pliocene is a way to look at what a warmer climate that was around for a long time, what that looked like. So these are just sort of artists' renditions of what we think the Pliocene looked like, right? So you should take this with a grain of salt. This is not actually a satellite image, it's just made to look like one. So the early Pliocene had very little ice on Greenland. The Antarctic ice sheets were probably smaller. And sea level, I put up here 20 to 30 meters, but I went to a Pliocene workshop last month. And it turns out that our uncertainty in sea level is pretty big. So this could be probably as small as 5 to 10 meters. It's probably more than, so the person I talked to who's sort of working on this most closely said, well, probably more than 10, but probably less than 30. Okay, it turns out it's hard to reconstruct sea level because those benthic isotopes are telling you both sea level and temperature. So it's hard to pull those signals apart. So this is our best guess. So I think in this rendition is 20 to 30 meters. So you can see Florida is kind of underwater. I think in the next one I sort of zoomed in on the picture in California. So Central Valley is sort of flooded. The other thing that in the Pliocene that we know that I'm going to show you the records of today is that the sea surface temperatures off of California were somewhere between 3 and 10 degrees warmer than they are today. So quite a bit warmer, and I'll show you those records and where the big changes were and where the smaller changes were. And then this is just showing you a side-by-side comparison of how different things really look, right? So this is what we think the Pliocene looked like. This is what we think the planet looks like during an ice age, during the last glacial maximum. Huge ice sheets here, and then this is what today looks like. So it's a different world. So when I say that we use the Pliocene to think about global warming, it's important to remember that it's as close to an analog as we're going to get, but it's not the same thing. It's not exactly the same planet. Things are different. We can learn lessons, but you can't draw an exact parallel. Okay, so now I'm going to come back to this figure. So this prediction that if you hold CO2 at 365 parts per million gives you an average global warming of somewhere, around 0.5 degree Celsius. You get a little bit of warming, but not that much. Now the Pliocene, when CO2 wasn't actually that much higher, seems to be somewhere between 3 and 4 degrees. So that sets up kind of a dilemma for us, right? Because something's off. Either our temperature estimates are wrong in the Pliocene, or there's something happening in the Pliocene that is causing those warmer temperatures that isn't in the models. The other thing that's important to remember is that this is 100 years of model data. That's not very long. So for example, one of the things that could be happening is that there are feedbacks that are happening on longer time scales, and that 100 years isn't actually enough time to come into equilibrium with all of those changes. So that's one possibility. But that's sort of the fundamental question is, well, why was the Pliocene warmer? And then what we want to look at is those patterns that I just pointed out, where you have temperature gradients from north to south, the meridional temperature gradients, right, warmer to colder, temperature gradients from the east to the west across the ocean basins, especially in the tropics, but also here at mid-latitudes you see that temperature gradient. So we want to look and see what are the patterns of the early Pliocene different from today, and if so, can that tell us something about what the mechanisms are that are important in Pliocene warmth? Okay, so let's look at the patterns. Before I tell you about the patterns, I'm going to tell you a little bit about how the data is generated, just so that you believe it a little bit. So all of the records that I'm going to show you all come from ODP or DSDP or IODP. They're all from the drilling program. This is the Droides resolution that drilled most of those. And the data that I'm going to show you is actually comes from two sources. One of them is the shells of foraminifera. That's what this is. So this little guy is a surface-dwelling foraminifera, likes to live in the surface layer of the ocean. Its shell is made out of calcium carbonate, and we can look at the chemistry of that shell, and I can tell you what temperature was. And then this is a coccolithophore, and I'll tell you a little bit about the proxy that we use for that one. So the way that the drilling works is actually really interesting. I have not been on one of these cruises, but I'm about to go in February and March. But the drilling technology is actually really amazing. So you have to realize the scale of this is sort of crazy. So you're in, let's say 4 kilometers of water, and you're going to send a drill down that's about yay big, and you're going to put it into the bottom of the ocean 4 kilometers down, and you drill 10 meters of mud, and you bring that 10 meters up on the ship, and then you have to get the same thing back into the same hole. So one scientist that gave a talk in our department said the analogy is, imagine standing on top of the 3-story building with a very long spaghetti noodle and trying to get the noodle into a hole the size of a pencil eraser, right? It's technologically, but I don't know how they do it exactly, but I'm excited to see it happen. But they put a big cone at the bottom of the oceans, and there's beacons that help guide it, and then the ship has engines sort of on the sides of it to really help it adjust, and then the string, and then they get it back into the same hole.
Why
So,
did they put it back?
So because you want to go deeper. So the deeper you go, the older the sediment, right?
How come you can't take stuff out and then just take more out to go deeper? Like,
So you have to go into the same hole to get the same, to go deeper, right?
Yeah.
Yeah. So it turns out that they lose a little bit of sediment every time that they do that. So if you imagine that this is the sediment-water interface, they drill the first 10 meters, and then they drill the next 10 meters.
Oh,
And chances are they kind of mess up a little bit right here. So they'll actually drill a hole right next to it, and on purpose they'll just go down a little bit, and then they'll drill the next 10 meters so that this is offset, so that you have that time interval well covered. So yeah, so you want to go down. I mean, they drill into more than a kilometer of sediment, so it's a lot. So you could be at the same site for days and days, just back in the same hole, bring it back up, back into the same hole, bring it back up. So this is them. This is the 10-meter core being brought up, and then they cut it into chunks that are 1.5 meters to make it more manageable. And that's what this is. So then they slice it in half, and then what you're looking at here is that sediment core that's been brought up. And then I like this picture because it shows just. What I should have done is included a map of all the places that they have drilled, because it's really impressive. But there's a tremendous amount of mud stored in these huge repositories. So this is at, I think this one is at Texas, although I think that I imagine they look pretty much the same. And each one of these little sleeves is 1.5 meters of sediment. So it's actually a tremendous resource of sediment and rocks too. They drill rocks too. It's not just all, it's not all about sediment. I only care about the sediment, but they do drill the rocks. So I show this picture because I'm about to tell you about some sort of geochemical tools that we use to reconstruct sea surface temperatures. But the nice thing about sediment cores is sometimes you don't need anything complex. I mean, if you looked at this core, you would immediately notice that there's this thing happening right here, right? I mean, you can't not see that. It turns out that this is the Paleocene Eocene thermal maximum. So this is all of this sediment here is all the younger stuff. This is all calcium carbonate. It's all foraminifera and coccoliths, and it's all lovely. And then this is the PETM, which they think was a rapid release of methane, and the methane goes into the atmosphere. It turns into CO2, the CO2 goes into the water, causes acidification, and that acidification causes a mass extinction of anything made out of calcium carbonate because all that calcium carbonate dissolves because the ocean is more acidic. And so you have a mass extinction event, and then this is the slow recovery. Okay, so the PETM is an interesting event because it's a mass release of carbon and then a follow-up recovery of that. But
What does that stand for?
the Paleocene Eocene thermal maximum. Yeah.
Can you tell just by a sample this size how many years has gone by?
So the dating of the sediment happens in a number of different ways. One of them is you can look at magnetic reversals. So you can use that as one way to date them. Biostratigraphy is another way that you can date them. So there are people on the ship who do foraminifera biostratigraphy, who do coccolith biostratigraphy, who do diatom biostratigraphy. And so this is the general idea here is that for certain indicator species, we have a good idea of at what age sediment they show up, and at what age. So there's a first occurrence, and then there's a last occurrence if they're no longer around. And so you use all of these things to try to start putting dates on things. Okay, that gives you a rough age model, and then generally in paleoceanography cruises, they will try to do a benthic oxygen isotope record to link it to the global record and put together an age model. So yeah. Attaching an age to these is not as simple as we'd all like it to be.
Sometimes complex.
Yeah. Okay, so now I'm going to tell you a little bit about the sea surface temperature proxies that I'm going to show you. So alkanones are organic biomarkers. They're called biomarkers because we know that they're only produced by coccolithophores. So this is E. huxleyi, which is a species that's present in the modern ocean. This species has not been around more than 200,000 years, but it's relatives, it's ancient relatives. We're all making these molecules. So this is a 37 carbon chain molecule, and this one, it's hard to see it, but this one has 2 double bonds, one right there, and one right there, and this one has 3 double bonds, 1, 2, 3. Okay, so it turns out that the ratio of the one with 2 double bonds, okay, that's what the 37-2 means, the amount of the one with 2 double bonds compared to the total, we call that the UK prime 37. This index, this ratio, is related to sea surface temperature. So somebody actually figured out on a cruise, they were just measuring stuff, organic stuff in the sediment. They were in the North Atlantic, they were doing a transect, and they noticed this trend in this molecule. So it's a really big molecule. So when you measure the organic molecules, you're looking at a gas chromatography, and the bigger the molecule, the longer it takes to come out of the instrument. And so this thing takes forever. It's like an hour. So you put your sample in, like an hour later, finally these big chunky molecules come out the other end. And so they're easy to spot because they're separate from all the other gunk. Okay? And what they noticed is that there's a small peak and a big peak. And they noticed that one peak was getting, as at first, in the warmer areas, the first peak was small, and the second peak was bigger. And as they got colder, the first peak got smaller, and the first peak got bigger, and the second one got smaller. And so they changed. And so they developed this index. So now that we know this, and now that it's been measured all over the place, we can now use this, and we can look at the ancient sediments, measure this ratio, and correlate it back to sea surface temperature. Of course, there's uncertainty, but that's the basic idea. The other proxy that we use is the magnesium-calcium ratio of foraminifera. Again, this particular species lives in the surface water. Its shell is made out of calcium carbonate. Magnesium, as a 2+ ion, can substitute in for calcium, and it turns out that the warmer it is, the more that happens. Okay? So this is a culturing study, so somebody is growing foraminifera very carefully and at controlled temperatures, and the warmer the temperature is, the more magnesium to calcium, the more magnesium is in there. So the same thing. We can then use that, look at the fossil record, measure the magnesium-calcium ratio, and then get temperature out of that. Okay, so let's actually look at some data. So this is a review paper by Fedorov et al. From 2013. I was a co-author on this. So these are all the sites that we put in that paper. I'm not going to show you the records for all of these. I'm just going to focus in on a couple of interesting groupings. So the first place I'm going to show you is a series of records from the subtropical upwelling areas. Okay, and I'm mostly going to focus in on the California margin because, hey, That's where we live. So this is a temperature record from 5 million years, again on the right, to today, and temperature here. And this is an Alkanone record, so this is that UK prime 37 index. And what you can see is that temperature from today is around 15 degrees Celsius, and in the Pliocene it was about 9 degrees warmer, which is huge. I mean, that's a huge, this is like 25, 26 degrees. That is toasty. That is some warm, warm water. That is a really different ocean. And I can plot on top of that a record from the Benguela Current. So this is the South Atlantic, but again, an area that's characterized by upwelling. Okay, so it's in the subtropics. It's characterized by the same sort of physical processes, and it shows, I mean, the similarity between those records is sort of striking, right? So same kind of temperature change. They're at a really similar latitude. So I can put together all of the temperature records from the subtropics. So this is the California margin, the Peru-Chile current, the Benguela current, and the Canary current, and all of them show that the temperatures in the Pliocene were warmer. And depending on where they are, so the closer they were to the tropics, the smaller the temperature change, and the further away, the larger the temperature change. So all of the coastal upwelling regions were warmer in the early Pliocene, between 3 and 10 degrees. So again, the further off the equator, the bigger the temperature change was. Okay, so let's think a little bit more, before I move on to other temperature records, I want to think a little bit more about why it could have been warmer along California and what the physical processes could be. So there's two things that are happening in off the coast of California. One is that you have the California current, which brings high latitude cooler water down. And then the other thing is that you have coastal upwelling. So the winds here tend to blow from north to south. That pushes water offshore because of the Coriolis effect. And that draws water from the subsurface up to the top. Not from like the deep, deep ocean, but from like 300 meters or so. That's sort of where your water is coming from. And that water is colder. But that water is not just colder, it's actually also nutrient rich. So it has a lot of nutrients. So the reason why California is such a productive, biologically productive region is because of this upwelling. Because we're bringing out that cold water that has a lot of nutrients in it. So the warmer temperatures at these sites could be related to a change in the strength of the California current, right? So if that was weaker, then it wouldn't bring down as much cool water. Or it could be related to changes in the strength of the upwelling. Okay, those are two options. This is just my little diagram of upwelling. Wind blows from north to south, water gets pushed offshore, and you bring up this cool nutrient-rich water. So the key with the upwelling is that if you had less intense upwelling, you would expect to see both warmer temperatures and reduced productivity. Those things in the modern ocean are really linked. Okay, upwelling, cold temperature, high productivity. So I looked at records of productivity. I looked at 3 different records. Alkanone mass accumulation rate, so in other words, how many of those organic molecules are in the sediment, organic carbon and phosphate mass accumulation rate, and from 5 million years to today. So if it was just a change in the upwelling, I would have expected these records to just go straight up, because temperature just went straight down, right? So as temperature goes straight down, we'd expect productivity to just go straight up. But that's actually not at all what we see, right? We see this like weird bump in the middle, but it's not correlated with temperature at all. So the productivity and the temperature are decoupled. And what that means is that, you see how the levels here in today are about the same as the Pliocene? What that means is that during the Pliocene, there must have been some upwelling. There's no other place for those nutrients to come from. So that physical process of the winds bringing up water, that had to have still been happening. And the way that you can get that is by upwelling warm water. I'm going to skip this one for now. Oh, I'm just going to say that what we did, so those temperature records were at site 1014 here, just south of Santa Barbara. And I'm going to show you some records from site 1022, which was up a little further north. It also shows a cooling. But what we did at this site is this is the only site in the California margin that has good preservation of the diatoms. So diatoms have silica shells, and they're not always well preserved in the sediment. and we looked at a couple of indicator species. We looked at these species, which are indicators of upwelling. These are diatoms that really like a lot of nutrients, and so they're only going to show up in environments where you have high upwelling. And then these are subarctic species. So if you have a lot of subarctic species, it means that the California current is bringing those suckers down, okay? And then the upwelling species means that you have upwelling. So we looked at to see if there was a change in either one of these. So the Characterized species is an indicator of upwelling strength, and you see that there's variability, but there's no like long-term trend. So there's no the abundance of this species doesn't show that there's any indication, any change in the strength of the upwelling. So this bug, by the way, it doesn't care about temperature. It just cares about nutrients. Okay? So this tells us that there wasn't a major change in the strength of the upwelling. And then this species is an indicator, is a subarctic species, and there's a little bit of an increase here, but not a big trend. So what that tells us is it's actually neither. It doesn't seem to be a strong change in upwelling, and it doesn't seem to be a strong change in the strength of the California current. So this is the alternative option. Okay, this is my lovely schematic of the vertical temperature distribution of the ocean. You have the warm surface ocean at the top, cooler deep waters in between, and then this is the thermocline for those non-oceanographers. The thermocline is just the gradient, where you have a steep change from warm surface to cooler subsurface water, okay? So I've drawn that this is 200 meters. I've drawn this really shallow because that's what it is in the modern California current. It's a pretty shallow thermocline, okay? So in the modern ocean, when you have upwelling, so when you blow winds across this kind of water, you're bringing up cooler water from below the thermocline up to the surface, okay? So what could be happening in the Pliocene is that you could have a deeper thermocline, and then the same strength of winds would still be bringing up water and still be upwelling, but the difference is that the upwelling would be bringing up warm water instead of cold water. So that's a possible scenario. So, so that's the summary of the subtropical upwelling regions, is that the California margin temperature was 3 to 10 degrees warmer in the early Pliocene, and that we think that the cooling was likely related to a change, not so much at the surface, but rather a change in the character of the subsurface water, the stuff that's being brought up to the surface. So that's subsurface water was warmer, and but still had nutrients in it. Okay, so now let's look at the tropical Pacific. So, I'm going to take this little water here. So the tropical Pacific, how many people have seen this diagram before? Oh, okay, all right, I will talk you through it. So this is, first let's get oriented. So this is North America, this is South America, this is Australia. Okay, so this is the tropical Pacific Ocean. The surface colors, the colors here at the top are representing sea surface temperatures. And then this blue line is representing the depth of the thermocline. So remember, the thermocline is that transition between the warm surface water and the colder, deeper waters. So today, under normal conditions, meaning not an El Nino year, but a normal year, what you have is water in the eastern equatorial Pacific that's cooler, and water in the western equatorial Pacific that's warmer. So you're looking at about 29 degrees Celsius here, and about 23, 24 degrees Celsius here. And the trade winds are blowing across along the equator, and the trade winds are basically pushing that water from the east to the west. There's no Coriolis effect on the equator, so when you just blow those winds across, if you just imagine a big bathtub and you stuck an industrial fan on one side of it and you turned it on, you would push the water away from your industrial fan and it would pile up on the other side. Okay? And that's literally what happens. So the water piles up on the western side. So the sea surface height is a little bit higher here than here, by about 1 to 2 meters. So somewhere between here and here. Okay, that doesn't seem like much when I'm just pointing it like this, but when you add up all that water across the entire Pacific Ocean, it's actually a lot of water. And it doesn't just push it up, it also pushes the thermocline down. So that the reason the thermocline is deeper here is because you're blowing all of that water over to the western side. So the thermocline is really deep in the western side, and it's shallow on the eastern side. Okay? So what happens during, during a normal year, sea surface temperature is 5 degrees cooler in the east than in the west, and the thermocline is shallow in the east and deep in the west. So what happens is during an El Nino year, those trade winds, they weaken. Sometimes they even reverse a little bit, and not for very long. We're talking about like a couple of weeks, okay? So they weaken or they reverse, and what happens is that, imagine you've got your industrial-sized fan, right? You've got it on, it's blowing the water to the other side, and you just turn your fan off. What's going to happen?
Slosh back.
It's going to slosh back. So that's basically what happens during El Nino. So all this giant pile of warm water sloshes across the tropical Pacific. The warm water is now distributed all along the tropical Pacific. The thermocline is deeper in the east. It tends to be a little shallower in the west. But so the end result of that is that sea surface temperatures in the east and the west Pacific are actually really similar during an El Nino year. So the east Pacific is really warm. And the thermocline deepens in the east. So when you think about El Nino events, you know, in California they mean changes in precipitation, but in the tropics here, it means much warmer temperatures, much wetter conditions, because this warm water is associated with convection and all the clouds and all the rainfall, right? So during a normal year, that's all sort of pushed over to the west, and the east is relatively dry. But during an El Nino year, those clouds come across, and you have wetter than normal conditions here. Not only that, but the fisheries all crash because the thermocline is so deep, right? So that when the trade winds are blowing, even when they pick up again, the thermocline is deep, so it doesn't bring up the nutrients, and the fisheries all crash. This is from the NOAA website, and it just shows, not every El Nino is created equal, okay? So these patterns don't show up with every single El Nino, but in general, these are the broad patterns that you expect to see during an El Nino event. You expect drier conditions here in the west, because all that source of rain has moved across, right? You have warmer and wetter conditions in the central and eastern tropical Pacific. And then you have all these, so these are like right at the heart of where all the action is, right? But then you have what we call teleconnections. Teleconnection is just a fancy word for saying like the atmosphere is connected. So we end up with changes in precipitation patterns here along California because it changes the location of the high pressure system that gives us our usually dry conditions, okay? Pacific Northwest tends to be warmer. So there's all these patterns that kind of showed up. And actually in the early 2000s, there was a paper where they looked at all the terrestrial data from the Pliocene, and they mapped it on top of this, and they were like, the pattern is actually really consistent with that. And so people started looking at, okay, well if the pattern is consistent, then the place to go to see if that's really happening is to the tropical Pacific, because that's where all the action is. So what I'm going to show you next is temperature records of the eastern Pacific and the western Pacific to see what that looked like. So the El Nino is really important because, and that pattern is really important, because when you do that, when you change that distribution of warm water, you change all these things in the atmosphere. Most importantly, you change how much water is in the atmosphere, which is a really strong greenhouse gas. So El Nino years are some of the warmest years on record because they warm the entire globe. So in terms of future climate change, this is actually a big question of how is El Nino going to change in the future. These are all, each one of these symbols represents a climate model. These are all different climate models. And if they are plotted to the right side of the center line, it means that the model result shows that on average, climate is going to be more El Nino-like, okay? And these show more La Nina-like. And then if it's plotted above the line, it means that there's going to be more El Nino variability, and below the line, there's going to be less El Nino variability. And you can see that it's not exactly a convincing story here, right? They're a little all over the place. And it turns out it's really hard to model the tropical Pacific. There's a lot of complex dynamics that are in those models, and it's a complex thing to model, and it's a complex thing to make sure that you're modeling it because you've got the physics right, rather than you're forcing it to give you the right answer. So this is an important question in terms of future climate change too. So I'm going to start out by showing you records from the eastern equatorial Pacific. So these are the sites here, and these are the different temperature records. So we've got different sites. So on this detailed map, these little speckles here are the Galapagos Islands. Okay, I've never been, but I'd like to go, so I like to point it out in hopes that that wins me some magic karma. And then we've got a site just north of it and a site just south of it. So these records are from two different proxies. So I've indicated them here. Two of them are from magnesium calcium, and two of them are from alkanones. And at this one site at 847, we have both records. So the black line is the alkanone record, and the red line is the magnesium calcium record at the same site. And if you look at it, you can see that the black and the red, it's kind of reddish pink, are basically right on top of each other, okay? And that's great news, because there's uncertainty in all of our temperature proxies. So anytime that the proxies tell us the same story, okay, thank you. And so what you can see is that all of the records show that the Pliocene was warmer. So the eastern equatorial Pacific was somewhere between 2 and 4 degrees warmer in the early Pliocene compared to today. Great, but now we have to look at the western Pacific. And it turns out that, so this is a figure that shows you those records in addition to a record from the tropical Atlantic, so other records from the tropic that basically show you the same thing. So the question, when you come back to this, is, sorry, I'm going to stop for a second. So there's two more things I'm going to show you. The first one is a record of the subsurface, what the subsurface looked like, and then we'll move to the western Pacific. So again, this is just as a reminder, so during a normal year, we'd expect the thermocline to be shallow in the east, and during an El Nino year, we'd expect it to be deeper in the east. Okay, so how do we get at that? We use this little guy. This is a foraminifera, tumida, and this guy likes to live at the base of the photic zone. So it tends to live at about 120 meters, which works out really well for us, because during a normal year, the thermocline is shallower than that, and during an El Nino year, it's approaching to be close to that. So this is a great tool to use to try to look at what the subsurface was doing. So this is going to be magnesium calcium record. So we've picked these little guys out of the sediment, and then we measure the magnesium calcium ratio. So I'm going to show you several records from both the east and the western Pacific. So this is from site 847 here, and you can see that there's warmer here. There's a big step here between let's see, what is that, 4 to 4.5. And we think that this is actually a change in the depth of the thermocline that's related to the closing of the Isthmus of Panama. So that matches that timing of about 4.5 million years or so. And you would expect that to cause a change in the thermocline when you close that seaway. The data from site 1241, you can see it's almost hard to see the two records because they're so much on top of each other. These came out of different labs, by the way, different places. And so what we think is when you think about this temperature record, if the bug is really living at the same depth, what it's recording is the thermocline getting shallower. Okay? And actually, we can look at records from the western Pacific, and you can see they don't have this big step, but those records actually also cool slowly through time. So this is what we think is happening. This is, again, a little schematic of the surface ocean versus the deep ocean. And this dotted line is sort of made to represent, this is the depth at which the winds can get to. So winds can only reach so deep to physically move water, right? So that's what the little dashed line is. So 5 million years ago, the east and the west had similar temperatures in the subsurface, right? They overlap. And so that means that there's basically no tilt to the thermocline. It's flat and it's deep. At 4 million years, you can see that they're separate, right? The eastern Pacific is colder, and the western Pacific is warmer. So now you have a tilt, but you see how I don't have it drawn up to the little dotted line? That's because we know that the sea surface temperature is still really warm. So it's not so shallow that the winds are bringing it to the surface, because the surface temperature is still really warm. And then finally today, you have a situation where it's really shallow in the east, and then deep in the west. Okay, so summary, the eastern equatorial Pacific, temperatures were 2 to 4 degrees warmer. The subsurface temperatures cool by 5 degrees, which is a lot for the subsurface. The productivity, I didn't show you these records, but they're the same as they are in the California margin, that there's no correlation with sea surface temperature. So the nutrients and the temperature are doing something completely different. And this is consistent with, it was a hypothesis proposed a while ago, that the thermocline is sort of gradually shoaling through time. So through the Cenozoic, through the last 60 million years, as the climate is getting colder and you're increasing the amount of ice at high latitudes, you cool the deep ocean, because that's where the deep water comes from, is from high latitudes. And when you do that, it pushes the thermocline up. So through that time, the thermocline is sort of gradually getting shallower. Okay, but we have to look at the warm pool. And the reason why the warm pool is really important here is that if climate is driven primarily by greenhouse gas forcings, then the east and the west sea surface respond the same. So if you take a climate model and you only increase greenhouse gas warming, the east and the west are both going to warm. So the gradient, the difference between them, is still there. Okay? So what the temperature is doing in the warm pool is actually really important. And here's what they're doing. They're not doing anything. It's like, more or less, it's just, each record is basically a flat line. So the Indo-Pacific warm pool and the Western Atlantic warm pool were not warmer in the early Pliocene compared to today. So when you put those two things together, what you see, and I've just taken a couple of the records, so the pink lines are the Indo-Pacific warm pool and the blue lines are all from the Eastern Equatorial Pacific. So what you can see is that they overlap in the Pliocene. So the temperatures in the east and the west are the same in the Pliocene. The east gets colder and the west basically doesn't change. So what it looks like is basically that this pattern of the east and the west being the same is sort of what the average climate looks like. We have to be careful here, though, in that it's not an El Nino. It's not a super El Nino. It's not a giant El Nino. It's not an El Nino. The El Nino is part of the El Nino Southern Oscillation. It's by its very definition an oscillation from El Nino to not El Nino. What we're saying is that the average climate, or the mean state of the climate, was different and resembles, that the pattern resembles an El Nino-like pattern. So we started calling it El Padre, although that hasn't really, it's sort of only quasi-caught on. Okay, so I feel like I'm running out of time. So I want to talk about what are the implications here. So remember, this is the question we wanted to answer, right? We wanted to say, okay, there's this difference between what the models think how much climate is going to warm with somewhat warmer CO2 versus compared to what we see in the Pliocene. So what are some of the possible mechanisms? So I'm going to go through a series of mechanisms that have been proposed for causing Pliocene warmth, okay? And then we'll look at the patterns that those result in and see if they match the patterns of the data. So remember that the patterns of the data was that we had a reduced zonal sea surface temperature gradient. So zonal just means east to west. We had a deeper thermocline all along the tropics, and there's new records coming out that show that's true not just in the tropics. So a deeper thermocline everywhere. We had stable sea surface temperatures in the warm pool. So we had the east was warmer, but the warm pool was not warmer. And then we also had reduced meridional temperature gradients. So we didn't really talk about that very much, but the temperatures here are quite a bit warmer. So the temperature difference between the tropics and the high latitudes is reduced. So the meridional temperature gradient is the same. So whatever mechanisms we look at for explaining Pliocene warmth needs to be able to explain all of these things. Okay, that's what we're looking for. That's the holy grail of Pliocene climate. Okay, so the first proposed mechanism is the effect of closing the Central American Seaway. Okay, so this is a model result of how climate looks different if you go from an open seaway to a closed seaway. So what you show is that you actually get quite a bit of warming at high latitudes, especially in the North Atlantic, and that's because you strengthen the Gulf Stream. When you close that seaway, you strengthen the Gulf Stream, more efficient transport of heat to high latitudes. But you don't really see a change in the thermocline depth. You see a little bit of a change in the East Pacific, but you don't see a change in the tropical sea surface temperature gradient. So this only explains a little bit of the meridional temperature gradient. So that's not the holy grail. Higher atmospheric CO2. So if you run a model and you increase the CO2 forcing, you do get reduced meridional temperature gradients, but not that much. So you get more warming at high latitudes, but it's not a huge amount. And then again, the tropical temperature gradient is maintained. So if you increase CO2, the east and the west move in sync with each other. They both warm, which is not what we observe. That's why that warm pool is so critical, because it doesn't show any warming. There's a hypothesis that you have increased ocean mixing. This is a model result of hurricanes. So this is a pattern of modern hurricanes and typhoons. And this is a pattern of if you take an atmospheric model and you say, it's just warm everywhere, okay? It's just warm in across the tropical oceans and at these latitudes, and you plug in what the temperature reconstructions look like, the model says, well, yeah, warm water generates lots of hurricanes, and that increases ocean mixing, and that transports heat around. So this, if you do this, if you increase the ocean mixing this way, you do get a reduced tropical sea surface temperature gradient. You do deepen the thermocline, and you do increase the meridional temperature gradient. But it's not quite, doesn't quite get all of the features correct. But this does seem to be playing somewhat of a role. The reduced extratropical low stratus clouds, I meant to talk about this when I showed the records of the upwelling regions. So those cool sea surface temperatures along the margin of California and where you have upwelling are characterized by low stratus clouds, these low-level clouds that are really reflective. If you warm that temperature, you get rid of those clouds, which means that you reduce the albedo in those regions and you absorb more incoming solar radiation, and that warms the climate. So if you get rid of those clouds, the model result is that you get a small reduction in the zonal and meridional temperature gradients, but you do increase the warm pool temperature, so that's not ideal, and you don't really get any change in the subsurface. So this is probably as close as we get. So this is my sort of final slide. If you run a model and you increase CO2 by 100 parts per million, you enhance ocean mixing, and you reduce the albedo of the low-level clouds, then you start to get really close to what the Pliocene actually looks like. So in terms of the mechanisms of what is causing Pliocene climate, it's probably a combination of all of these things. And this feeds back into thinking about how this relates to modern climate, because, for example, the east to west temperature gradient, some of the models see that gradient reducing, some of the models don't see the gradient reducing, right? And if you don't get rid of that temperature gradient, you don't get some of these important feedbacks like the cyclones and the stratus clouds and things like that. So, okay, so I think I'm going to end there. I'm going to acknowledge my co-authors, Christina Rebello, who's my PhD advisor, Alexei Fedorov and Chris Brierley, who are at Yale, and Kira Lawrence, who's a colleague. My student did all the diatom work in collaboration with a couple of other people, and then the funding for the work was sort of a combination of NSF and ACS, PRF, and Fusion Building, all that stuff. And I will take questions.